real pleasure to introduce today's speaker, especially because it doesn't really need much of introduction. David Gross, well, he did his PhD in Berkeley in '66, and after spending a couple of years at Harvard, spent much part of his career at Princeton afterwards, and then moved to KITP Santa Barbara in '97. And many of us know him really as a face of that beautiful institution. But of course, in addition to that, he also the father of theory of strong interactions, which as I'm sure we'll learn from David right now. It's one of the most beautiful and one of the most perfect theories which we have in physics. It's really the goal which we're trying to achieve in many other areas of physics. And I think it's quite unique to hear about birth of a theory and the history of a theory for somebody who actually is a father of the theory, created that theory 50 years ago. The 50 years have been counted from 1973 paper by David Frank Wilczek. And well, I should say that David is not new to NYU. He was a close lecturer here in 2014. And so hopefully we'll hear a very nice update about the status of QCD from him. Well, and finally, obviously, David received lots of awards, most notably the Nobel Prize for the discovery of QCD. So without further ado, let David speak. Thank you for being here.
Before I start, there are places for those of you standing in the back, right in the front here, if you wish to sit. And second, I've already lost 10 minutes. But otherwise, thanks for the invitation and the introduction. This has been a very full 2 days here. As great evidence that QCD is alive and kicking, and we're working hard. Many young people are involved in trying to solve some of the problems that remain even after 50 years. So, this indeed is 50th anniversary of QCD. And I'm going to largely discuss the history and the current status, some of the prospects, but largely history of QCD. And it's nice to celebrate 50 years of anniversary, especially to an audience. I think, well, this is an unusually old audience. But I would say half of you were not alive 50 years ago. And you know, it's also very close to 100th anniversary of quantum mechanics, which is coming up in 2 years, which we're all going to celebrate. And on the occasion of the 50th anniversary of QCD, I think back what I thought of quantum mechanics 50 years ago. Seemed awfully far back. Okay, my screen is not so visible at the bottom. But I'm going to start at the very beginning of QCD, of strong interactions of the nuclear force, which is now 112 years ago, was Rutherford's famous experiment, where he discovered the nucleus, discovered the structure of the atom, led to quantum mechanics, and he invented elementary particle physics, experimental elementary particle physics. 3 great discoveries, worthy of 3 Nobel Prizes. Rutherford got a Nobel Prize in chemistry, of all things, for radioactivity, died too early to get 3 more, which he deserved. So the famous Rutherford experiment was how to look inside an atom. He figured the best way was to shoot alpha particles, which he had been playing around with for years, at gold atoms in a gold foil, and then they would scatter, and he would try to figure out what was going on inside the atom, which really nobody had any good idea, remarkably, in 1911. And so his students, postdoc and undergraduate students, sat in dark room and detected the scintillations of the deflected alpha particles. Remarkably, instead of just mostly going in the four directions, some of them came right back at large angles, very surprising. And Rutherford, with the help of some of his mathematical friends, I gather, calculated the Rutherford cross-section and figured out where the positive charge of the nucleus was located and concluded that it was in a very small region, 1/10⁴ size of the atom. He couldn't even determine the radius of the nucleus, just a upper bound, lower bound, upper bound. Had to be smaller than something, he couldn't determine it. And well, that was an amazing discovery of two things. One, the nucleus, most of the mass, most and all the positive charge of the nucleus of the atom is located in this teeny little region, the nucleus, and that immediately led to a picture of the atom, a planetary description of electrons circulating around the sun, the nucleus. That in of itself was so surprising and classically inconsistent with the stability of matter that it led within 2 years for a young postdoc at Rutherford's lab to come up with a Bohr model of the atom where quantum mechanics stabilized the atom. And that was such a successful description of hydrogen and quantitatively calculate the Rydberg constant, qualitatively the periodic table and the beginning of atomic and molecular physics, and the creator of severe paradoxes that were resolved only 14 years later, mostly by theorists, very little extra experimental information with quantum mechanics as we know it today. So, nucleus, the planetary model of the nucleus, which led to of the atom, which led to quantum mechanics. But our story, most importantly, is the nucleus. The Rutherford really sort of discovered the proton, identified the nucleus of hydrogen as a particle inside the nuclei, only in the 20s. And Chadwick only discovered the neutron in the 30s. So it took almost 20 years to even begin to identify the constituents of nuclei. And with the tools available at the time and the total lack of any theory, things progressed kind of slowly. But very importantly, the third contribution of the Rutherford experiment was to develop the technique to do particle physics, to explore the structure of matter at very short distances, to construct a nuclear microscope, which we figured out, figure out what goes on inside the nucleus, inside the atom, probe short distances, use scatter particles off your target or off each other eventually. And that remains our tool for probing short distance of matter ever since. Of course, we have much bigger accelerators. There's no pointer in here, there at the LHC. And our detectors have progressed substantially from a scintillating screen. They're much more complicated. But the basic idea of how to probe the short distance structure of matter that we continue to employ today was invented by Rutherford. And now, well, perhaps we have to do something else. These accelerators, these detectors are becoming very expensive, employing thousands of people, dozens of years to construct. Maybe we need something beyond Rutherford, but nobody's been so far able to come up with a new idea. Okay, so when I was a graduate student, I was a grad student at Berkeley, which at that time was the center of elementary particle physics for a short period. At the largest accelerator in the world, 6 GeV, 1,000 times more than the LHC. But it was an amazing instrument, which was discovering new particles every month. It was clear by that time that there were really two forces acting inside the nucleus, the strong force, which held the nuclei together, and the weak force, which was responsible for radioactivity. The strong force was especially intractable. Nobody had really any good idea, so that was what attracted me, because there was no good theory at all. And but there were a lot of experiments going on. And at that point in time, there was absolutely no idea what the elementary particles inside the nucleus were. Protons and neutrons, additionally, it was thought. And then the pi meson, which was invented by Yukawa as the massive short-range carrier of the nuclear force and observed in the 50s. But the new particles that were being discovered all the time looked exactly the same as protons and neutrons, just heavier and unstable because of radioactivity. But there was nothing special, particularly, it seemed, about protons, neutrons, and pi. And then, of course, there was absolutely no principle as to what the dynamic should be. Unlike, quantum electrodynamics, the incredibly successful quantum theory of electricity and magnetism, there was a principle understood by Maxwell. All you had to do in the 50s with quantum field theory, developments of quantum field theory, was quantize Maxwell's theory. But here there was no theory to quantize and no principle that was known. And then even if you had a principle, it was clear that the strong force was strong, a very powerful force. And so it was unlikely that any perturbative way of calculating, even if you had a theory of interacting ions and nucleons and so on, you could do any calculation. So it really was intractable. Dyson famously remarked that the correct theory will not be found in the next 100 years. Now, this is a good lesson for some young people. Dyson was one of the main contributors to QED. And after that success, he and others tried very hard to construct a quantum field theory of ions and nucleons that would explain the strong nuclear force. And he failed miserably after trying very hard for a few years. And so he gave up. But when physicists give up, they usually explain their failure by statements like this, thereby excusing them from any responsibility. And of course, he was off by 87 years. The general feeling was that a revolution was needed, something really different. Something probably not explained by current theory. Now, in retrospect, the reason why this was such a difficult problem is clear. The charges of the quantum chromodynamic field that we now understand is responsible for the nuclear force, the color of quarks and gluons, were completely hidden. The constituents were completely hidden. Very unlike atomic physics. There, electrons were discovered before the atom was understood. They were obviously inside the atom. Rutherford discovered the nucleus. You could see the charged particles that were the source of the electromagnetic field that held atoms and molecules together. But in the case of strong interactions, we now understand the basic constituents are quarks, gluons, and they're completely hidden. So atoms are easily ionizable. You hit an atom, electrons come out, they run in wires, do work, and that's how they were discovered, knocked out of atoms. But when you collided particles together, quarks never came out. Just more protons, hadrons, heavy particles like protons and neutrons. So that made it kind of difficult. The other reason it was very difficult was that quantum field theory, by that time, well, it was relativistic quantum mechanics, understood very well by then for quantum electrodynamics, polarization was understood, how to calculate weak coupling. In the case of QED, you could calculate observables, test them with experimental theory worked brilliantly. But that theoretical framework of quantized quantum field theory was under severe attack. Renormalization was invented to deal with the UV divergences of QED, but most of my teachers and the inventors of quantum field theory thought it was a trick. There was something inherently wrong with quantum field theory. Somehow you were sweeping the things under the rug. It was a sign you really didn't understand what was going on. Dirac thought just quantum field theory nonsense. You know, he invented it. In addition, quantum field theory really wasn't very understood at all. Particularly, there were no useful non-perturbative methods at all, or even non-perturbative formulations of the theory. So my first course I took in quantum field theory was from Steven Weinberg. He walked into the class and wrote on the blackboard, field theory equals Feynman diagrams. That was what field theory was at the time. Now, there was a quantum field theory, what we today would call an effective field theory, phenomenological effective field theory, good or low energies for the weak interactions, Fermi's theory, current, or theory of the weak interactions was quite successful. But, you know, given that successful effective field theory, nobody had any idea. Many attempts, all of them, failures to unitarize it, make it unitary, consistent at higher energies. It was not a renormalizable starting point. Again, quantum field theory did not seem to work. Yang-Mills theory, the hero of all of this, of course, in the end, was formulated in 1954 by Yang and Mills, but it was plagued with massless gauge bosons and never seen, of course, and nobody knew how to deal with that at the time. And but that didn't stop people from immediately trying to apply Yang-Mills theory to strong interactions. Now you needed a symmetry. Well, there wasn't any obvious exact symmetry, so they coupled the gauge currents of Yang-Mills theory to approximate symmetries, which is inconsistent. Nonetheless, they did it, coupled it to the approximate accidental flavor symmetries, which were all the rage, isospin, SU3, and so on. That made no sense, as people discovered pretty fast, so it didn't work. Then there was a very strong attack on quantum field theory as such. I said a revolution was needed, something was really quantum field theory. It was believed by many to be rotten at its core. My advisor in Berkeley was Jeffrey Chu, who was the leader of the West Coast of the United States of this attack on quantum field theory, based on two principles. One was nuclear democracy. He's very good at inventing names, Jeff. All hadrons are equally fundamental. Now, well, this is what the experiment showed. We produced lots of hadrons, dozens and dozens, and they all seem equally fundamental. So why assume that there are only one or two of them and all the others are bound states? In fact, you could always choose a bunch of them and or try to argue that all the others were bound states of those, but you could choose another bunch. So his answer was all hadrons are equally fundamental. So you're not trying to construct a model of matter based on a few elementary constituents, treat them all equal, all perhaps infinite number would see equally fundamental. That's a pretty radical idea. And how then can you construct a theory? So the idea was, I'm not going to write down a Hamiltonian with an infinite number of equal or a Lagrangian or anything, but just it was so hard to find a consistent relativistic S matrix anyway that perhaps if you just impose general constraints that embody obviously true principles that we're never going to give up, like causality or unitarity, the fact that probabilities that you calculate add up to one, that those general principles are so hard to implement in reality, very few, if any, sort of four-dimensional theories that embody those principles were known, that you just impose those general principles and perhaps there's the unique solution. So that's the bootstrap theory, bootstrap approach. And you constrained it later on as this developed by various regularities that people discovered phenomenologically in nature, like symmetries, or global symmetries, or wedging behavior, asymptotic. In the Soviet Union, which was separated from Berkeley by a Iron Curtain, there was a totally different attack on quantum field theory known as the problem of zero charge or the Landau pull. And that was the conclusion of the Landau school, Landau and collaborators who studied trying to go beyond just low order perturbation theory, quantum electrodynamics. And in particular, they studied the relation, normalization, if you want, but the relation between the physically defined coupling of the theory, defined as the coupling between charged particles at arbitrarily small distances, what is called in quantum field theory the bare coupling, E naught, and the physical coupling, 1/137, that you measure at macroscopic distances. As you let the ultraviolet cutoff, you needed to introduce always in perturbative treatments of quantum field theory a cutoff in order to render finite the otherwise ultraviolet infinities. And so then the bare coupling, you could then calculate, in principle, the physical coupling in terms of the parameter that you introduced to define the coupling at short distances. And what they found in leading order, leading log order, or summing leading logs and quantum electrodynamics and a bunch of other theories was what is called a zero charge, or the Landau pull. So this is, in their crude first approximation, the relation between the physical coupling that you measure, the bare coupling you put in as you take this ultraviolet cutoff to infinity. And you can see that no matter what charge, what bare coupling you put in, you know, as you let the cutoff go to infinity, the physical coupling vanishes. Well, that says, okay, you can construct the quantum field theory, but the charge will always be zero, electrons will be free, trivial theory. We believe actually that's true for QED. Nobody's proved it yet. It's true. It's also called the Landau pull because you can turn this around and ask, well, we know what the physical coupling is, and now we explore what the bare coupling does as we try to remove the cutoff. So as you vary lambda, you're going to get to a point where this logarithm becomes negative, this denominator Yeah, if I turn this around and express E naught in terms of P, you'll see that as you reduce log lambda, as you make log lambda big enough, there comes a point where E naught has to, where EP diverges. What it really means is that in some observables, you're going to find a singularity which violates causality.
Sorry, would it be not divergence? Or EP fixed?
No, EP divergence. As you keep E naught fixed, I think the cutoff. If you keep EP fixed and take lambda to infinity, the only way that can happen, of course, is that E naught diverges at some log lambda equals 1 over EP squared. Log lambda equals 1 over P squared, lambda goes like e to the 1 over EP squared. That's the lambda pole. But it really is, better way is to regard this as the zero charge. No matter how strong you make the bare coupling that defines the theory, physical charges vanish, the theory is trivial. And of course, this has a very simple physical explanation. It's simply screening. If you put a charge into a medium, we know that it is screened. By screening, you have dipoles. A dielectric medium will screen charges. And that, in a relativistic quantum field theory, the vacuum itself is a medium. It's full of virtual pairs of particles that can be present for a short time. And so vacuum in quantum field theory is a medium. And in the case of QED, the medium consists of electron and positron pairs. And these dipoles align and screen the external charge you put in. So if you put in a charge, a bare charge, the electric force decreases. There's more screening at large distances. In fact, so much so that you might argue that it vanishes microscopically, increases as you go towards the charge, less screening at short distances. So this phenomenon is simply screening, and that's very physical. And this, in fact, is true. It appears for all non-asymptotic theories, this problem of this screening is so strong that the charges vanish. And for example, it is widely believed this is true for QED by itself. If you just took quantum electrodynamics, it probably doesn't exist. That's been proved for simpler four-dimensional non-asymptotic theories like phi-4 theory now. Hasn't yet been proved for QED, but will be in 50 years, I predict. Landau concluded that within the limits of formal electrodynamics, by which he sort of meant quantum field theory, a point interaction is the equivalent for any intensity whatsoever to no interaction at all, zero charge. And he came to the conclusion the Hamiltonian or Lagrangian quantum field theory approach, where the strong interaction is dead and must be buried, although of course with conservative honor. Now, Landau made a statement for the strong interaction. Also true for QED, which is what he studied. But for QED, if you ask what is the ultraviolet scale where this happens, it's so high energy, so much higher than the Planck mass, that he understood, well, gravity, who knows what will come in, it's irrelevant. But the strong interaction starts out strong. And if you go go to higher and higher energies, you're going to get to the regime of this Landau pole and nonsense. So he was a strong personality in the Soviet Union, and he forbade his postdocs and his colleagues and students. One of whom is right here, who can tell you that.
I disobeyed.
Tried to, yes, you did, but you had to. So the young people like Sasha, and Sasha Boyakov, they were not allowed to work in quantum field theory, and they cheated by saying they were working on many body. Meanwhile, experiment was blooming. The theory was in the process of sort of shooting, giving up everything that was firm, and experiments keep happening. And there was great experimental excitement. Berkeley was a very exciting place. There were new particles and new patterns of particles, new approximate symmetries which were discovered, and new phenomena like Reggie behavior and so on. But experimenters were confused as well. Another interesting lesson. Many theorists and experimenters believed that the secret of the strong interactions lay in the high energy behavior of scattering amplitudes at low momentum transfer. Diffraction scattering, the total cross section. That was always the big deal. You had a new accelerator, measure the total cross section. What was it doing? It's still constant or increasing or whatever. Nowadays, you can barely find an experimenter at the LHC who wants to measure the total cross section. No one's interested. Everyone understands to discover new physics, you look at very hard events, large angle scattering. That's how you look at probe for short distances. Diffraction scattering, large impact parameters, simply measure exchange of light particles. Not interesting. Quite the opposite back then. Theorists discovered regularities, Reggie behavior. So they told experimenters, this is interesting. Experimenters love that because there's so much more data for scattering the forward direction. They didn't have very high intensity accelerators. They loved the idea that you should focus on the regime where there's a lot of data. Statistics gets better. So they continued to promote each other in the wrong direction. So experimenters and theorists can all go wrong, often reinforcing each other's misconceptions. These were experimentally interesting, easy experiments, interesting patterns were discovered. No one particularly was interested in high momentum transfer, where, as it turned out, the secret of the strong interactions were to be found. Now, I escaped from Berkeley and the bootstrap and went off to Harvard, and there quantum field theory was tolerated, and I started playing around with currents, or what is now called operator product expansions, which I learned from Durkheim, largely could be directly probed in deep elastic scattering of leptons or hadrons, and using totally inadmissible, nonsensical free field theory rule results derived all sorts of sum rules. This was a period in time where, since there was no real theory and no real foundation, quantum field theory was all, you were allowed to do anything as long as you could make a prediction. And in those days, if you made predictions, you could be sure that they could be tested within a few months or a year. They're totally different than today. Now our standards are tough. And again, to the young people, new crazy ideas are often not tolerated because we know so much, and experiments take 50 years. That we can't rest on nature to override the objections of your elders. Anyway, we derived all sorts of sum rules. Durkheim realized that these suggest scaling, which is, free field theory has no scale. But some of these sum rules were really interesting, like we could derive a sum rule that told us how to determine, if you look inside the proton, the spin of whatever it's made of, if it's made of constituents. Anyway, I was all set to be ready for an experiment, the crucial experiment in the development of QCD, which is deep inelastic scattering. So in 1967, I think, 68, a new accelerator opened at SLAC, which could scatter 20 GeV electrons, not very energetic, off stationary photons, but measure the cross-section for large angles scattering, in effect scattering virtual photons with large momentum squared, negative minimum squared off photons, which is a microscope of what is inside short distances, short time intervals, the structure, whatever it is that makes up the nuclei. Now, this is so reminiscent of Rutherford, going back, was now 60 years before. Before Rutherford, everybody thought the nucleon was this complicated jelly gas, who knows what. And the same was sort of the feeling about the proton. People have measured the electromagnetic form factor of the nucleon. So it's all spread out over the proton radius. And people expected that in deep inelastic scattering, where you're not just doing elastic scattering, but producing an arbitrary number of hitting the proton with a proton producing anything, inclusive cross-section, you'll discover some smeared out behavior, just like in the case of elastic scattering. And it was, I gather, it wasn't that everybody was clamoring to do the total cross-section inclusive scattering. No, only a few people were. They, of course, were the people who discovered that the proton looked as if it were made out of atoms, freely moving quarks. They were the people, from my point of view, demonstrated that scaling, free point-like behavior, quark model sum rules work. They were the people who were awarded the Nobel Prize for discovering quarks. Most of the experimenters were interested, as most experimenters in particle physics are always interested in seeing bubbles. They don't want to see these processes. The SLAC people, Friedman, Bindle, and Taylor, didn't see a bubble. They didn't discover a new particle. They discovered indirectly that, much like Rutherford, what the basic constituents of the hadrons were. But this was extremely confusing. To me, the experiment and my some rules, some of that we derived that worked, convinced me that hadrons were made out of point-like constituents of these were quarks. But how could that be? Because these sum rules, for example, only derived all the results by assuming the quarks were totally free. No indication of what their interactions were. We treat them as free particles. And why don't you knock them out of the proton? How could that possibly be? How could you explain scaling on the one hand and the fact that you never produce quarks, confinement on the other? And so people first started this study a new symmetry of nature, scaling symmetry, conformal symmetry, which one discovered is often accompanies just scale invariance in quantum field theory. But immediately one realizes that classical scale invariant theories are not scale invariant once we turn on quantum effects. Quantum effects destroy scaling. For example, QED, that whole screening, right? There's no scale in QED except the mass of the electron. You could ignore that as short. But the dynamics itself depends on distance. More screening at larger distances, less screening at shorter distances. Anyway, personally, I must say I was fascinating detour to string theory. That what appeared to be a revolutionary theory, which maybe could explain everything. But it was obvious to me after a while that strings, being very soft, extended objects, could not explain the hard point-like behavior seen in deeper resonance. So by 1972, I had a very specific plan. I was going to destroy quantum field theory once and for all. And the plan was simple. I would simply take scaling, exact scaling, as an experimental fact. Most of my friends didn't go that far, and they believe, for example, Ken Wilson, that this was an epiphenomenon, low energies, very bad statistics. I mean, it was just temporary. You'd start seeing best of anomalous scaling, anomalous dimensions, as we would say today, or some other behavior. You got to reasonably high energies. Take the scaling as experimental fact, and then use what we know about what by then, largely to Wilson, about non-perturbative quantum field theory to show that asymptotic freedom is required to explain scale. And then simply, and a large part of that was accomplished by Callan and I for most quantum field theories, not non-revealing gauge theories, but really you do need asymptotic freedom to explain scaling. And you don't even get exact scaling, you only get a logarithmic approach to scaling. And then second, then asymptotically free theories simply do not exist. And there was some hope of proving that, because if you have asymptotic freedom, which means that when you go to very short distances, the couplings turn off, then perturbation theory becomes reliable, more and more reliable if you go shorter and shorter distances. And so you can use perturbation theory, and there are only a countable number of normalizable quantum field theories anyway. So you have a chance of proving, or not, or that they don't exist, or maybe finding one that does exist. And proved with the help of Sidney Coleman that actually there is no sensible field theory with any number of scalar or spin 1/2 or abelian gauge spin 1 with arbitrary that are renormalizable is asymptotically free. The one theory that didn't really fit in was new, being then understood that much better, was Yang-Mills theory for the electroweak interactions, but not perturbatively, still difficult to study. The proof that you needed asymptotic freedom broke down in any case. And the calculation required more work. That's where Frank came in. That was my first graduate student. And I have one more hole to fill. Let's work and calculate the ultraviolet behavior of non-revealing gauge theories. And this is paper, and a little more now than 50 years ago, in which remarkably we found that they possess what does. To me, it was an enormous surprise. I truly expected this too, like everything else, would fail. And that would be the end of quantum field theory. Nobody, of course, would agree with me. I would have been satisfied. But anyway, the gauge theories, non-revealing gauge theories were different. They asymptotically free. And therefore, we should look to a non-revealing gauge theory of strong interactions to explain the European scaling. the amazing thing was, well, for me, it was just a total surprise, but once it was there, everything was obvious. Totally obvious. There was really no choice. The dynamics had to be, everything else was, you couldn't stick anything else into the theory except Gangwell's theory, because otherwise you'd lose this property of asymptotic freedom. So the dynamics is obvious. The matter, we know for years what the matter was. Quarks, the sum rules, inelastic scattering made it clear. Fractionally charged quarks in 1/2. Color had already been invented to understand the statistics of hadrons built out of quarks. So there was really no choice. At that point, there were only 3 triplets, up, down, and strange. The other 3 quarks had not yet been discovered. SU3 color gauge group, that was it. No choice. QCD. Now, why does QCD, why is it asymptotically free? Well, this is anti-screening. And the best way to understand it physically, although we didn't, that was not the original one, originally just calculated, was virtual, from a magnetic point of view, screening is diamagnetism. When you just have, say, QED. But in the case of non-abelian gauge theories, the big difference is that the gluons themselves are charged. They have a big charge. They have a quark anti-quark charge. 8 colors. 8 red anti-blue. It's 3 times 3 minus 1 is 8. So when you put in an external magnetic moment into QCD vacuum, these little gluon permanent magnetic moments align. That's called paramagnetism. And that increases at large distances. Get more parallel magnets, decreases at short distances. Just the opposite of diamagnetism, the Lenz's law, or dielectric behavior. That's the physics of it. Now, retrospect, I can wonder now why Landau, the master of kinetic physics, didn't understand that what problem he had encountered mathematically, physically, was just screening, dielectric, diamagnetism, and he could have said, okay, well, I need a theory. Paramagnetism, how do I get that? I need virtual like little magnets. I need spin 1. I don't know, he could have. No. In our larger paper, right, in those days, by the way, physical review letters restrict you to 2.5 pages. Religiously, they cut out half of our original paper. But a few months later, we published a paper where we started to do many things, like calculate. The great thing about this theory was coupling was small at short distances, at high energies. You could calculate using perturbation theory. So we calculated the deviations from scaling and the elastic scattering QCD. But also we started to address this problem of why don't you see the quarks? The general feeling, originally of ours as well, was that, well, non-abelian gauge theories had to be broken spontaneously, had to be a Higgs mechanism. That's why you don't see the gluons. But that made no sense. And certainly from the point of view of demanding asymptotic freedom, didn't make sense because the scalars you'd have to, Higgs bosons you'd have to introduce, Higgs field would destroy asymptotic freedom. Anyway, so he said, okay, symmetry is not broken, it's exact. But then why don't you see the particles? So coupling got strong. That seemed to give us the hope that these expectations could be quite wrong. There might be little connection between the free Lagrangian and the spectrum of asymptotic states, particles you observe, and Whatever happens is determined by the strong coupling limit of the theory, whatever it is. Confinement. Well, that was at least originally reassuring as a goal, but became and still is the main issue facing QCD. Now, we of course know that quarks are confined. We know that first and foremost by experiment. We now smash particles together at 1,000 times the energy of back then, and still no one, except Fairbanks for a while, Stanford, where they tend to find things like monopoles or found them. Nobody's ever seen them before. Second of all, from of course theory. Now, a kind of physics term, solve QCD numerically, and we don't need and quarks are good confined. But still, truly understanding that, and especially the sense of having a controllable analytical quantitative description of the infrared behavior of QCD remains an open problem that hopefully will be solved in this century. And we've started to do that in the Simons collaboration, which just had a marvelous 2 days of exciting new insights. This is a difficult issue. How do we think it works? Well, in a abelian theory, a theory like QED, a non-confining theory, if you try to separate two charged particles, use Gauss's law to determine how the field strength, the work it takes, the energy it takes to separate, saturates at the ionization energy, and you could ionize atoms. In the case of the strong interaction, the strong force is motivated by a very similar force law, and classically it gives rise to naively to a 1 over r potential, 1 over r squared force. And but a medium obviously plays this important role. That's what gives rise to this ferromagnetic vacuum that's confined. And what we believe happens is that vacuum forces these flux lines, does not tolerate electric field. It's sort of the electric version of, it's a magnetic version, the dual version of superconductivity, which is a kind of superconductor, where magnetic field lines are squeezed to tubes. That's the Meissner effect. In this case, electric lines are squeezed to a tube. The area you integrate over now in Gauss's law is fixed. So the electric field on this area is the charge, and the magnitude of the electric field is constant. It doesn't depend on distance. So the force between the quarks does not decrease as you pull them apart, and the amount of energy it takes increases without that. That's confinement. That we believe is the mechanism for confinement, and but it's not been proved. $1 million in the bank for anybody to prove it. And well, we have lots of evidence. This is lattice QCD calculation. What happens when you pull apart two heavy quarks? See, the flux is confined to this tube, which has roughly constant area, and leading to this linear potential growth of energy between the separated quarks. Okay. Now back to a bit of history. So QCD burst in 1973 into the thing, for a small group of people, whom I call smart people, it was immediately accepted. They said, ah, that explains it. That explains just about everything. And indeed, just about all the features that we learned over the years about the strong force could easily be recognized or made a part of QCD. There were some issues, some problems, which is always good, something to work on, and those were rapidly resolved. Realize there was another parameter, but all sorts of interesting developments. And the beginnings of trying to construct models of confinement and other theories like superconductivity, voiding, and so on. But this is a group of people who, I must say, immediately responded positively, and then started to calculate. I mean, there's nothing physics like more than to calculate. And in QCD, okay, you could immediately calculate, sometimes not justifiably, sometimes very justifiably, and increasing arguments why it was justified to treat certain processes perturbatively, but you could just do perturbation theory. A lot of people had to learn about Yang-Mills theory. Believe me, nobody knew about Yang-Mills theory by and large, certainly beyond the three of us. But that was pretty straightforward. Slow and steady growth, so a lot of interesting calculations that began immediately, a lot of theoretical milestones, which were very important for solidifying the fact that you could have a theory like this without elementary particles that you could see. I used to have enormous arguments with my colleague at the time, Eugene Pigner, who said it was totally nonsense, base the theory on to have a theory of physical theory where the elementary particles could never be produced as asymptotic states. Because that was his definition of what an elementary particle was. It was an irreducible representation, unitary representation of the Poincare group. So you had to see it as an asymptotic state. It was hard to really swallow that. Lattice gauge theory was invented a year later by Ken Wilson, the beginning of an incredibly powerful numerical tool for studying Colloquium in general. And in the case of QCD, a strong coupling regime, which is the opposite of what you really need, because you take the lattice space into zero, the coupling has to vanish. But in the strong coupling regime, you saw immediately, trivially, confinement and the strings, these flux tubes, which look like the strings of strong coupling. I was very pleased by being able to solve a asymptotically free two-dimensional theory, which you could see developed a dynamical mass gap, a dimensional transportation occurred, everything was fine. And it also solved large N two-dimensional QCD, well, where although confinement is sort of trivial because you have linear confinement and two dimensions kinematically, still, this was the first time it was sort of like QCD, where you could see a theory in which the basic constituents, the quarks, were confined and not present as asymptotic states, but at short distances you could see them moving freely. Very nice. But the real turnaround in QCD happened, as always, in physics with experiment. So electron-positron annihilation was one of these observables. Electron-positron total cross-section, easy to measure if you have an electron-positron collider, like at SLAB, donut, many places throughout the world. And simple arguments, scaling, and certainly in QCD, you could predict what the ratio of E plus E minus goes to hadrons compared to E plus E minus goes to electrons. Simply was a measure of the sum of the squares of the fundamental constituents. which were 3 quarks with fractional charges. And this was the prediction, and it worked beautifully. One of the arguments for 3 colors, even before QCD. But 1974, at a conference in Trieste, so young days of QCD, I gave a talk on QCD had to be the theory of the strong interaction, same arguments as I did, scaling, da, da, da. Up stands Bert Richter and says, well, yeah, but we're beginning to look more closely at this region. And you blow it up, it doesn't look so constant. Looks, in fact, like this ratio is increasing. Goodbye scaling. Goodbye QCD. Experimenters love to do that. They haven't been very successful for the last 50 years. They still love to do that. They just, anyway.
Seems a little
Now,
unfair.
some of us said, well, maybe you're seeing charm. In fact, a smart physicist knew that there had to be other quarks in addition to the 3 observed quarks. For many reasons. Electroweak theory made no sense without a charm quark, and so on. In fact, Appelquist and Pollitzer did a nice calculation of what a charm anti-charm meson would look like. And because of in QCD, because of asymptotic weak coupling, it would be rather narrow resonance. They didn't predict it off by maybe a factor of 10. Actually, turns out to be much narrower than they discussed. But you know, theorists at that time, again, unlike today, were very timid and shy, tentative. They hadn't had much success for the last 30 years. So they, anyway, Richter went back to Slack, and of course, as you know, the situation changed dramatically within a few months. They discovered the James Line particle and other Chromodynamic resonances. There were zillions of papers, well, dozens. Half of them were total nonsense, the other half were QCD, and which worked. This totally changed everything for a much larger class of people. And of course, this has been a marvelous tool for identifying, again, the basic charged constituents, new quarks, and then eventually electroweak as a gauge particle as well. Okay. Asymptotic free and flow. Well, what about testing QCD itself? Well, this is a situation 16 years after the theory was proposed. It kind of, this is how the strong coupling decreases as you go to higher energies or shorter distances. Looks like it agrees with the theory of all sorts of different experiments. But you know, a straight line fits perfectly well. Using tests in QCD turned out to be extremely difficult because you're looking for what? Easy experiments, the ones that are easily interpretable by perturbative QCD and logarithmic effects. And logarithms very, very strong. This is what it looks like in 2012. By now we have calculations that are accurate to 1%. Credible agreement with perturbative QCD in the whole range, including both jet production, trillion. This is the decrease of the strong coupling, one of the more recent, 2014. Still 40 years later, and this is quite amazing by now, at much less than 1% agreement in literally dozens of high precision experiments, all fit by one parameter. This is deviations. This is rather old from things we calculate immediately, deviations from scaling. Again, small effects until you go to very small x of the inelastic standards, still from Hera. These are sort of an example of recent LHC tests of QCD. Most of what QCD does is test QCD. Most of what LHC does. So experimental evidence now overwhelming. But what, of course, the theorists wanted, what I wanted to do originally was to solve QCD, calculate the mass spectrum of the hadrons. That's hard. A vacuum is complicated. And the only real quantitative first principle controllable tool we have is numerical, that is QCD. But it's turned out to be an incredibly precise tool by now. But it too took 40 years. This approach was really championed in the early 80s by Ken Wilson originally, who gave up and said, impossible, it's too hard. But people like Michael Kreutz continued, and 40 years has led us to this kind of ability to calculate the hadron spectrum, the masses of all those particles that are being discovered when I was a graduate student, to a sort of 1% accuracy across the board. This required improvement by 18 orders of magnitude in the power of this calculational tool. 9 of those came simply from Moore's law, didn't come from us. It came from the guys who developed these. But 9 orders of magnitude came from theoretical ingenuity, better understanding of how to write down a lattice version of QCD, better understanding of how to incorporate finite size effects, how to incorporate fermions, et cetera, better algorithms. So it's been estimated, it's not my calculation, that 9, factor of 10 to the 9 improvement in calculation techniques. So it's quite amazing that it required this factor. Again, QCD is not trivial. Also, there have been unbelievably impressive calculations in perturbative QCD. It used to be hard to calculate loop diagrams, analysis, the techniques, the structure, the new relations, partly inspired, by the way, by string theory, have led to an unbelievable advance in our ability to do perturbative calculations. I don't have time to talk about them. In addition to the leading order calculations that we did months after QCD was born, next to leading order turned out to be really necessary to get going, but now one goes next to leading order, next to leading order for very complicated processes that absolutely require not just to test QCD, but that use QCD to calculate the backgrounds to whatever new physics, like the Higgs discovery, could never have been made without precise control of the background to Higgs production. We look at the discovery of the QC of the Higgs particle, you see a little bump above what is expected. But what is expected to mean what is calculated with some estimate of errors quite precisely. Now, I want to end by discussing QCD as a perfect theory, very, very perfect in 3 senses. First of all, these ultraviolet affinities that people, the founders of QFT worried about simply aren't there. Second, there are no parameters. QCD is the first example of a theory you have with essentially no adjustable parameters. And it's also the first theory we have of no physics at short distances, no limitations if it was only by itself. So no infinities. So, this pair coupling which diverge, QED, vanishes, right? Infinities only occur in QCD if you try to express observables measured at finite distances in terms of those measured into these fourth distances. In lattice gauge theory, where one actually constructs the theory as a limit of a theory of a lattice of size A, and writes down the answer, and then takes a continuum limit where A goes to 0 and the volume goes to infinity, you introduce this coupling which measures the theory at short distances. And then asymptotic tells you how to take the continuum limit. You let G go to 0, take A to 0, you measure an observable at a finite distance, you get a finite limit. No infinities ever appear, no need to introduce counter terms or anything. Simply no infinities. It's a bad way to figure out. This probably doesn't work for non-asymptotic, unless you're very lucky, but so there are no UV divergences, really. Second, there are really no finite parameters, no true parameters.
PR, HQF by Nexus, Zarek, ADEF,
Oh,
from
right.
Nightfocos.
So Feynman gave a beautiful talk in 1961 after about a decade of QED, greatly successful. He summarized the theory, the agreement with experiment. Then he tried to ask himself, can quantum electrodynamics be really a final theory of QED? So he tried to, QED has two parameters, prime structure constant, 1/137, and the mass of the electron, which sets a scale. So two parameters, he wanted to calculate, like most physicists, everything. So it set the mass of the electron equal to 0. Maybe we can explain it dynamically. Okay, that's not easy because mass electron goes to 0, there's a chiral. He understood that you would have to break a symmetry, chiral symmetry spontaneously. Bamboo, I've begun to explain that. But then he said, okay, pure QED, 0 mass electrons, just photons, can't produce an electron mass because the system is scale invariant. So if there's no scale, there's no parameter to determine a length or a mass. So I'm not certain. Feynman was always careful. Not certain, but it appears to me impossible to generate a specific length or a mass from a no-scale theory, whatever. You couldn't calculate ME or alpha for that matter. But then he should have known this. Quantum effects break scale and can produce a physical mass scale and thereby determine the coupling at that scale. And that's what QCD does. So it's a theory with no adjustable parameters. Now, of course, in the real world, there were these annoying quark masses, which come from the Higgs sector, which we don't understand. Okay, gotta measure them, but they're not particularly important for low-lying hadrons anyway. There's also there are parameters like the number of colors, for example. 3, Y3, but no other parameters, no adjustable parameters. If you consider the proton has a mass. Doesn't come from the quark masses, they can be set to 0. It comes from the growth of the force. So these quarks rattle around, try to get away from each other, right? Pressure, but the force increases. At some point, they're confined. That defines a scale, a length, a mass. Now, of course, that's the quarks are massless. There's no length, just like in 2D. So that length, you can simply say the proton mass is the mass I will use to define masses, energy, or inverse length. And then the coupling is determined. It's the coupling that produces that. And so, in terms of one length, which you have to always choose, make measurements, you could call it one if you want. The strong coupling is capital. So QCD, through this process of dimensional transmutation, if you want, from no length produces a length, and then capital coupling. And in particular, all mass ratios, all dimensionless parameters, QCD, if you have no quark masses, are numbers that depend on nothing. They can be calculated. The final perfect, beautiful feature of QCD, which again is the first time this happened in physics, is that the theory has no limitation when you go to arbitrarily high energies. Every one of our previous theories, including Maxwell's theory, had a problem with the electron self-mass. Always something bad happens at short distances or high energies. But not in QCD. Asymptotic in QCD becomes simpler, just perturbation theory. And that had one immediate application, very strong, very important, for cosmologists and astronomers, who at that time, CMB was about 10 years old, well established. They were pushing to try to understand the early universe before CMB. But they were faced with a prospect of what a colleague of mine called hadron hell. Just imagine dense nuclei. Nobody knew anything about nuclear physics. But according to QCD, you go to higher density, early universe, higher temperatures. That's where the theory, we believe, deconfines, gets phase transition perhaps to a quark gluon phase, but maybe one that ultimately is treatable by perturbation theory. So instead of an unknown mess, a simple perturbative regime. And that certainly motivated the ability to go beyond the first 3 minutes to the first 3 Planck times. And of course, thinking along those lines, immediately opened up the fact that, okay, what happens if you heat QCD? Or you create dense quark matter? And it was clear that, if you heat up the system, energies get bigger. You're reaching the region where you could use perturbation theory. In perturbation theory, quarks are confined, so we expect a phase transition to a deconfined phase, same thing with density. This now has become an enormously big field of nuclear physics. Nuclear physics has taken over low energy QCD in the interesting dynamical regime of high temperature and high chemical potential, dense matter to with experiments and theory to probe the phase diagram of QCD as a function of temperature. And finally, the fact that QCD becomes simple at high energies encourages one to extrapolate all of the standard model then understood to high energy. And the remarkable discovery of Weinberg, Quinn, and Georgia was that just trivial extrapolation based on standard model was that these forces, two things, the forces tend to come together at very high energy, the same place gravity becomes a strong quantum force, and that the multiplets of matter that were known then and later fit together so neatly as to strongly, still remains for me the strongest clue that all the forces we know, maybe there are other ones that appear in between, are unified at close to the Planck scale. That, of course, was a big push towards string theory, which seemed to have the capability of doing that. And finally, this asymptotic freedom kind of explains one of the outstanding large number problems of physics, which Dirac emphasized in 1937. Numbers like proton mass compared to the Planck mass, 10 to the minus plus 20, or many other such numbers of the same order of magnitude. Dirac really puzzled by this because he thought you could never explain them, but you might be able to relate them. So he postulated all sorts of relations between this kind of number and say that radius of the universe compared to the radius of the atom. Now, he could have said, well, we understand why this is so small. Because if this was just one part in 1,000, we wouldn't be here, right? We would be black holes. This is the reason why gravity is so weak at our scale. And so, unless that was true, we wouldn't be here, and then we couldn't ask the question. That's why it's true. That's the proper argument. Dirac was too smart to make such arguments. But he did suggest that if all these numbers are related, some of them vary with time. So maybe Newton's constant, Planck's structure constant, vary with time. The cosmological scale, that's been disproved pretty much by things like billion-year-old nuclear reactors. But this problem is really solved by QCD in the sense that we assume that at very high energies, the Planck scale, things are unifying, and the coupling, the strong coupling, is of order, what it is from our extrapolation, or QED coupling, something reasonable, 1/20, 1/60, doesn't matter particularly. How are you going to calculate the proton mass? Well, at very high energies, the coupling is very weak, quarks are combined. We've got to pull them apart. This varies very logarithmically. You have to go to very low energies to get to the region where the quarks interact strongly enough to be confined. That determines the scale of the proton. And therefore, the ratio goes like logarithmic. The log of this, you solve the problem by taking the log, but that's what the theory tells you. That's why it's so hard to test. And roughly speaking, with what we know, that's the right number. That's why, of course, unification works. But it really does explain my satisfaction, this small number, and offers hope for explaining all the other small numbers. One of the reasons supersymmetry is so attractive, because it could explain, for example, the Higgs mass that way. That might not work. But in any case, having explained one of these 10 to the minus 20, the optimistic among us, including me, can hope that the rest will follow. Maybe it'll take another 50 years. For you young guys who might be around then, try. Anyway, so QCD is really perfect. It's the first example of a complete theory, no adjustable parameters in essence, no negation of a distance scale where it must break down, infinite bandwidth from low energies to arbitrarily high energies. But of course, there are these other parameters in the theory, and there's gravity and the other forces of the standard law. The most interesting part, really, perhaps in the long run of PCB, is its connection to string theory. Evident from these flux tools, explaining why the string theory came out of phenomenological attempts to understand the strong interaction. Features of the strong interactions, many of them are indicative of these flux tools. That's why string theory was developed. Of course, in string theory, once you have open strings that might describe mesons like this, you also have closed strings, gravitons, as it turned out. Gauge theory might be equal to string theory, or related, but that string theory includes gravity. Now, that connection has been greatly strengthened the last 25 years by our greater understanding of the duality between different theories, including between quantum field theory in flat space, just like standard model, UCD, supersymmetric theories in particular seem to be dual to string theories in anti-de Sitter space, which offers some hope. For example, that we might be able indeed to solve, in some sense, or get a quantitative control of the QCD. For example, one of the possibilities is that the maximally supersymmetric cousin of QCD, which is dual to a simple string theory, could be solved, and one is getting pretty close to that, at least for a large number of colors. And then one could try to deform that theory. There's a continuous kind of path in theory space to less supersymmetric theories, or even real QCD. It include quarks. Again, small effects for a large number of colors, but one could expand. Anyway, all of that is hope. There are many other hopes. And given the vitality of the science collaboration to just witness last 2 days, my hopes have increased for you guys, 50 years. In the future, there's going to be clearly great developments at the perturbative level. It's unbelievable what has been discovered recently, the last miracle. And the many open time-dependent issues that are remain really in QCD, including argumentation, action scattering, etc. Experimentally, LHC was built to discover particles. There was one particle that was predicted and was found, the Higgs, but it's discovered like 50 other particles. Some people have even paid attention to this. These are multi-quark states. They've been discovered 40 years ago. This would be a big deal. It still is a big deal. They're really very interesting. LHCb and other such experiments will continue to explore interesting quark states. ALICE and soon the EIC will continue to explore the behavior of quark matter, of dense nuclear matter. This is really fascinating stuff. EIC is deep and elastic scattering, but now at incredibly large momentum transfers, and not just off protons, but off nuclei as well. So let me just end with, Feynman was once asked, Feynman once said, I had to summarize physics for all of scientific knowledge to the next generation of creatures, either ChatGPT or cockroach. What statement will contain the most information in the fewest words? And he did a fantastic job, only Feynman could do that. I'd say atomic hypothesis. One sentence, no equation. All things are made of atoms, little particles that move around in perpetual motion, attracting each other, when they're a little distance apart, but if you're trying to squeeze them more, they repel. A lot of physics you can understand just from that. The cockroaches could go on. So what have we done from the standard model in one sentence? Can't do it. I can do it in one slide, however. We learned that matter is made of charged and fermions. Forces are described by a gauge field theory, quantum gauge field theory, which has three phases: electromagnetism, Coulomb phase, long range, symmetry is unbroken, U1 symmetry, weak interactions, SU2, gauge theory, screened or Higgs by a very unnatural scalar field sector, strong interactions, SU3, gauge, confined phase. What have we learned after 50 years from QCD? Again, one sentence, one slide. Well, most important, we've learned that it is the theory of the force. Second, that dynamics can actually determine everything. All masses and couplings. We can be ambitious. And most importantly, perhaps, gauge strength duality. So I'm going to end with a hero of all of this. The hero of this PCB, hero of the standard model, dual, perhaps the hero or the equivalent dual description of string theory, and therefore the origin of what space-time is. And I'll finally end, but not the end. Thank you.
It was very inspiring talk. So we'll go to refreshments and have discussion there, but there are some very urgent questions.
Well, interesting.
I have a little comment about Landau, because I happen to be one of the oldest guys in the audience, surprisingly. And I was there when Landau was thinking about both quantum field theory and the solid state physics and turbulence. The thing is that he did not realize the relation between the two. That's why he did not understand that phenomena he knew very well in solid state physics do not apply to quantum theory. He was
No, but and no one did at the time. It was a remarkable period for whatever very interesting reasons. Condenser physics and quantum field theory, elementary particle physics were really totally separate. One looked down on the other,
yes.
which was also it was disastrous intellectually. It was just as true in the West as it was, as you would say. But I would have thought that Landau, who made seminal contributions to both, would have been above it. But not.
It was not.
That is.
Well, of course, it is extremely inspiring and wonderful. But you didn't mention axions.
No, I did so many things I didn't.
No, but what specifically I'm raising the point about, this has to do with a strong CP problem you didn't mention. As you were speaking, I thought to myself, I mean, QCD really does see perfect. But QCD by itself,
I didn't discuss the fact, by the way, the theta parameter, with my colleagues Callan and Nasher, we introduced the theta parameter puzzle. Or once instant algebra. So, yeah, QCD is another parameter. I didn't discuss it. Give me another half an hour.
no, but really,
It's great. Yes, I can see, but I've already gone half an hour.
No more questions. We'll continue at the department at the wine and cheese, the usual place.